Okay, it'd be great to start with a little bit of background on the company. I suppose the sort of when, why formed, a little bit about yourself and other key personnel. I know, for example, I think you've appointed fairly recent Dr. Drew Nelson. So just, yeah, give us a flavour of the company.
Yeah, that's absolutely right. My name's Mark Rushworth, CEO and co-founder of Finchetto. I formed Finchetto in earnest with Michael Piercy back in 2021, beginning of 2021. He's the technical co-founder, is the CTO of the company. He's a graduate in computer science, and he's also a specialist in non-traditional compute techniques. Yeah, you're absolutely right. Drew Nelson came on board as a non-executive director recently. He's a phenomenal character in the UK semiconductor scene, founded advanced wafer manufacturer IQE. He's a fantastic presence and advisor to the board. We founded Finchetto at the beginning of 2021 on the back of some ideas that Mike had, particularly in compute. The idea was to use a domain of optics or photonics to perform arithmetic and logic entirely in the optical domain. And so that formed the subject of our first patent, which is granted in the UK. And it also was is what generated the first few prototypes that we made. So we built an all optical arithmetic logic unit, so a part of a computer processor that performs all of the maths and the logic functions, developed the prototypes. The interesting thing is when we took that to customers, the need was actually not in the compute, but in the network, is what we found. And so that was where, because what generally happens is over time you've got this sort of balance between whether the compute or the network is in ascendance at any one particular time. And compute at the moment is in ascendance and networks lagging behind. And so what we looked at was how we might be able to solve that with the technology. So we developed, as a result of that conversation with customers, the world's first entirely passive network switch. And so that what I mean by passive, by the way, is there's no electronic control of the switching whatsoever. It's all done optically. And so that's been the subject of the focus in the last 5 or so years.
Okay, and we're going to obviously have a look at that technology in a bit more detail. But before we do, I guess, and you've explained eloquently, and with my storage background, I might add that it's compute, networks, and storage. There's always a
Yeah,
bottleneck somewhere in the system.
yeah,
But no, so to your point, it'd just be good to understand your take on the data center sector in terms of there is this huge exploding AI demand. There's sort of the need to try and control power consumption and address sustainability. So just the characterize the challenges, if you will, as to what's, how big is the problem, if you like.
sure. Um, I mean, I find the area fascinating because you've got a combination of an infrastructure and a business challenge all wrapped into one. So, I mean, the history of compute tells you there's always appetite for more compute. And I think unless we get to the point where you've got a digital twin of the universe, which I'm pretty sure somebody will tell me is impossible, Shannon, perhaps, you're always going to want more compute, always going to want more compute. But what we've got with the AI boom is this kind of mass market shock. So you've got a mass market use case that uses heavy, heavy computation. But it's all happening at once. And the thing is that what you've got is a cloud compute infrastructure that's being asked to give massive compute resource for the purpose of AI to the population. And that's putting stress and strain on the existing infrastructure and forcing us to grow faster than we might otherwise have done. So that's number one. And then the second thing is that the compute that you're using and storage and network for the AI networks is the most performant you can find. So the GPUs and the CPUs, and they are consuming vast amounts of energy. So, the stats that I see are 2 to 3% of the world's energy is used by data centers. That's increasing. And, there's a huge amount that's specific to AI. But in a world that so far has been economically and sustainability wise more or less balanced. I tread carefully there because I think it's probably less balanced. But on energy from carbon intensive sources, you've suddenly got this massive overlaid demand, and that's causing some fairly existential questions, which is what you're referring to in the question. And I think my concern is that delivering on that demand will take precedence over delivering it sustainably. You would hope that sustainability will catch up, but given it seems that compute is this era's space race, that's not a given. And so that is exactly what we're trying to solve at Finchetto, though, is higher performance at lower power. That is our aim.
Yeah, so in terms of the network specifically, network switches, etc., I guess first, how important is their role? As we discussed, you got compute, network, storage, all sort of interlinked, etc. But and I suppose at the moment, how much of a bottleneck is the net? Now, I mean, I can't remember to the top of my head, but this sort of 400 to 800 gig ether, all these. I don't know if that's even close to what AI needs, but what's the lag, if you like, between the AI compute capacity and where networks are?
Yeah, well, network switches are exactly that. They are the bottleneck. Okay, and you know how I was sort of saying that compute in the ascendance and networks behind. One of the reasons for this is that you have the compute sending out data in the optical domain from these optical transceivers, and that hits a network switch. Let's say it's going out on Ethernet, so standard protocol. It's going out in the optical domain. It hits a transceiver in a switch, and that converts it to electronics. And then there's a high performance processor inside the switch that's trying to figure out where that data needs to go. Once it's figured out where it needs to go, it then gets converted back to optics and sent on its way. But you've got this optoelectronic optical conversion, this OEO conversion in the passage of the data through the network. And that conversion has two impacts on the network. One is that it consumes time to go between the domains. So that's latency. So that's how fast you can transfer data from one side to the other. And the second, it consumes a lot of power. So that is where a large amount of the bottleneck is felt, is this conversion. And what impact that has is if you look at even the most performant supercomputers, the utilization rates, the amount that the compute is operating at any one point in time, is only at 1%. You're not using these compute resources as much as you could. So you've got supercomputers operating at a utilization rate of roughly 1% and deep learning at around 30%. So if you could unblock that network, you could use less compute nodes for the same performance, or you could use the same number of compute nodes for greater performance. So that's the key issue, unblocking that network. And then, of course, by eliminating that optoelectronic optical conversion, you can also reduce the energy consumption of the network fabric, which, again, anecdotally, is contributing somewhere between 10 and 20% of an entire data center's energy consumption.
Okay, so in terms of developing the fully optical passive network switch, uh, how easy was it? I mean, you say obviously you developed a sort of solution for a different problem and then understood where you needed to go. So if you can just tell us a little bit about that journey, were there any particular challenges to overcome? You knew where you had to get and how to get there? Just how easy was it to arrive where we are now, I suppose?
Yeah, I mean, when you're talking about deep tech solutions, nothing's ever easy, right? And that's the beauty of them because you're working on something that people haven't considered before. It's the first time you're doing it. Massive barriers to entry from a commercial perspective, which is good for a resource-constrained startup. And yeah, it's absolutely very difficult. What we've done is we've eliminated the electronic control of the switching. And so what we're doing is we're using light to control light. And that's the big technical step, the big difference between what we've got and patented and what others have. Now, normally light doesn't interact with light, so that's how you've got multiple different wavelengths going down a fiber optic cable. But if you set up the system in such a way, you can use a particular area of optics photonics called nonlinear photonics, where you can force light to interact with light. And we're using that to control the switching. So you're able to control the direction of the light, which way it goes, the data, with a control signal that is by light. So that is step number one. That's the base technology. That's what we had to prove and proved. The second, and that's the easy bit actually. Creating an optical switch, in inverted commas, is the easy bit. Creating a switch that plays nicely in a system, a network, that has been developed iteratively over decades with protocols like Ethernet, InfiniBand, whatever else that everybody is used to. That's the difficult bit. So that's where we've spent a lot of time focusing on how do we deliver something that operates in a revolutionary way, but fits in with the existing infrastructure. And that's been the key.
Okay, and in terms of the benefits, I mean, I think you've explained what they are, but do you have any, I mean, numbers, comparisons, in terms of reduced power, latency, etc., factors of or percentages, or is it obviously it'll slightly be dependent on workloads and stuff, but just yeah, where you think you might be able to get to, or you are at the moment?
Yeah, absolutely. So the two key metrics, you're absolutely right, are latency and power consumption for our perspective, and switching speed is the other key bit. We're actually, so as I say, you've got this light-based control signal, and you're switching light with light. So your reconfiguration speed or your switching speed is the speed that you can put the light into the nonlinear circuit, right? So you're literally switching at the speed of the surrounding transceivers. That's a key benefit, right? The second is the latency. Now, the latency is really interesting because the latency, the time the data takes to get through the network, for us, because there is no buffering, because there's no conversion between optics and electronics, because you've not got memory and internal storage as you describe, it is the amount of time the light takes to get through the system. It's the propagation delay of the light. So the smaller you can make that switch, the lower the latency. At the moment, we're still in fiber-based systems, we're talking orders of magnitude, so tens of times better latency than existing state of the art. But we're also developing alongside that a photonic integrated circuit, which is miniaturizing everything down to a chip that's the size of your thumbnail, right? And at that point, you're talking thousands of times lower latency, so massive improvement. And then, of course, power. Now, to drive light, it's a lot less energy intensive than it is to drive electricity. So again, tens of times lower power for a 48 port switch that's in development at the moment. We're talking operating at around about 40 watts in comparison to state of the art operating at around 2 kilowatts. Yeah.
Okay, that's intriguing. And in terms of the work you're doing, is it purely yourselves, or you got some key partners that are helping you? Just yeah, who is in your radar, if you like, in terms of uh, code? Because I guess obviously you can do it yourself, but as you say, it's got to fit inside a system, and then inside a data center, etc., etc. So just yeah, who are the folks you're working with?
Yeah, absolutely. So, well, I mean, one thing is we are a startup, so we're early stage, and I think from a credibility perspective, and also from our perspective, we don't want to be marking our own homework. So actually working with partners is super important. So we have two development partners, one on the datacom side, one on the telecom side. The telecom side, we've recently completed a piece of work which has been grant funded by the UK government to the tune of £1 million to develop a switch for the telecoms industry. And on the datacom side, we've developed good links with one of the major US corporates through an accelerator program that we were on a couple of years ago. But the focus now is to really get our prototype to a pre-commercial version, and that's in the coming months. And with that, what we want to do is we want to take that into prospective customers' laboratories and develop into proof of concepts and pilot networks. And we're talking to industry at the moment and inviting conversations. There's quite a lot of interest to have a look at this switch and really take it out for a test ride.
And in terms, I'm presuming those partners have been excited, encouraged by what they see. The feedback generally has been positive, or has it been helpful to work with them? Have they sort of been able to give you feedback and input to help, or is it pretty much they've been able to rubber stamp where what you thought was the right solution, if you like?
It's been a combination. It's been definitely been discursive. They are extremely excited about what we're developing. They see it as the future. They see the acute need for the technology in the way that I've described, unblocking that network. What we're looking at trying to achieve is massive networks, tens of thousands of nodes that are all interoperable. And you want a situation where if you think about I don't know, 50,000 compute nodes in a data center from one end of the data center to the next. You want the latency between the furthest to the nearest to be so low that you can't tell that it's outside of your rack, and that's what we're really working on. So no, they are super excited, and you know we're very very lucky to have had the development conversation because they brought the use cases to us to develop for.
And in terms of the whole sort of optical computing, silicon photonics, uh, sort of on a slightly larger scale, what do you think is the potential? Because as you say, it's a very disruptive, changing, sort of decades of thinking, if you like. And at the moment, clearly, it's aimed at the very high performance compute level. Uh, how do you see it, moving forwards? Will it sort of trickle down as a lot of these developments start sort of there and then come down more into the mainstream? But just your thoughts, I suppose, as to how, the potential for what you're doing and optical compute more generally.
Yeah. So okay. So at the highest level in terms of photonics or optics as a sector, the opportunity is massive, absolutely huge. The way I look at it is that photonics is kind of where electronics was in the 70s. You've made a lot of progress, and it's been on a specific use case, which has been telecoms and transceivers and fiber optic cables, right? But the potential for operating in the optical domain is huge. So, as an industry, I think as a sector, I think it's massive. Talking about optical compute and communications specifically, you've got you've got multiple sort of angles of attack using optics at the moment, the things that are in development. There's the switching side, which is what we've talked about primarily today. But then there's the optical interconnect side as well, and there's different levels of optical interconnect. So the simplest optical interconnect that everybody knows about is the fiber optic cable. But then as you miniaturize that fiber optic cable down to something that exists at chip level, you start calling it something different. You call it an interposer. And that is something where you're actually talking from the side of a silicon chip to the other side of the silicon chip. So you're really miniature at that point. So that's a huge area of interest because it means that the latency on the chip can be brought right down. And then you've got varying degrees in between. And then, of course, even in the fiber optic macro level, you've got different technologies that are being developed, such as hollow core fiber, which is lowering the latency of the transmission path by eliminating the glass in the core of the fiber and just having it as air. So then your light's just traveling through air. So you've got it super low latency. So there's quite a number of areas that are in development at the moment and show huge promise. But I think backing up to why is everybody excited about this? It comes back to the comment that many people have made before me, which is the end of Moore's law, and is silicon electronics butting up against a wall of development progress? And I think the answer is yes, in terms of the pace that we've seen over the last few decades. Not absolutely. There will always be more tricks that can be pulled. But in terms of the pace, yes, it's running out of steam. So everybody, of course, next looks to the next best thing, and that is optics.
Okay, and in terms of yourselves and the roadmap, I think you said you're sort of looking at prototypes and getting them out there, people to sort of kick the tires, etc. Do you have sort of other IP and solutions that you're and I can't not have a conversation with you without mentioning quantum computing, which I know is perhaps being a little bit greedy because that's the next big thing, but I assume that's not unknown to you as well. You're already looking vaguely at that. So just any plans, obviously you don't want to give away anything too much, but just anything you can share as to the future for yourselves.
Oh, no, absolutely. It's not greedy at all. Let's be greedy. So Finchetto has been part of a program, government-sponsored program called Cubic, which is the quantum business incubator run out of the Harwell campus, which is the UK's government scientific labs. And what the objective there was to figure out whether our switching technology could support the quantum supply chain. And I think the answer is that, in terms of the existing technology that's been filed, and you can read the patent, it's public, that isn't directly applicable to a quantum switch in the sense that if you had entangled photons and you wanted to send them left or right, that's not something that we would excel in because of the way that the optics works. However, However, there is a situation where even in the quantum supply chain, if you're talking about QKD networks, quantum key distribution networks, you've got a situation where the key, the encryption key, is delivered in the quantum manner, but then the data is all encrypted classically and sent in a classical scenario. So of course our switch would be highly applicable there. So yeah, there's what we have filed, what we have developed from is a base technology. It's a broad method and apparatus patent. It's not a design patent that can be used for any format of optical switching, provided certain circumstances are met. So data comms is key, AI is key, high performance compute is key. And that can be applied to multiple use cases.
And I'm guessing as well the future, I mean, can't move in the IT industry for the word hybrid being, attached to almost everything. And presumably this is another case potentially, things like co-packaged optics and stuff, where rather than just one technology being used everywhere, but there'll be nuances. So you'll use the best fit for each, and whether those are assembled together or whatever, it won't just be something taking over. As I say, depending on the application, cost, etc., there'll be a variety. So is that the future that you see?
Yeah, absolutely. I mean, even if you say optical switch, right, which we've kind of neatly used as the catch-all phrase, there's many different types of optical switches, right? But the two areas of optical switching are circuit switching and packet switching. So circuit switching is where you have a network set up for an extended period of time. So let's say that, a major content provider wants to send the latest 4 or 8K movie to the edge. Yeah. You've got an extended period where that link is up. And you don't need to change, you don't need to switch it left and right that often. It's just, on a path. Now, circuit switching is very capable of doing that. And so Google, for example, brought out or released papers on a switch they called Apollo, which is an array of microscopic mirrors that they can angle electronically. So you can reflect the data using the mirror from the input port to the output port, and it keeps the data in the optical domain, which is fantastic from a latency perspective. The issue is that the reconfiguration time or the re-angling of these mirrors is slow. It's in the tens of seconds. And what that means is that you can't switch on a packet by packet basis using that technology. You can't send one Ethernet packet this way and the next one that way because it's not fast enough. In order to do that, you need something called a packet switch, which has been entirely electro-optical to date. Now, what we've got, because we've eliminated the electronics from the switch, is the capability of performing packet switching entirely in the optical domain. And that's a big area. So our real focus, our value to the customer is the ability to perform all optical packet switching. Others are focused on circuit switching, and it's much, much smaller, but it is a use case. But it's the important thing is being able to switch on a packet by packet basis, and that's our differentiator, and that's what we do. So hybrid was your question. Yes, there's lots of different sort of formats and ways that you can create systems, and hybrid applies to quantum. Hybrid is quantum classical in the quantum sense. In the data center sense, yes, you've got interposers, you've got interconnects, you've got switches. The switches come as circuit switches and packet switches. And the way that you comprise that, I mean, there's some very, very clever people that build networks. The way that you comprise that and take all of the elements and build the full network is how you make something successful. But you need a bit of everything at different points.
It's been absolutely great to chat to you. Fascinating insights, and I've learned something that I expect everyone else watching and listening will do as well. But at least for now, Mark, really appreciate your time. Maybe we can touch base later in the year when you've got some feedback from trials and stuff. But at least for now, thanks for your time. Appreciate it.
It's been a pleasure. Thank you.